Hello, everyone. So last time we were looking at an application for second order differential equations. So basically we look at harmonic oscillations or mechanical vibrations. Harmonic oscillations. So we saw that we can write the equation of the motion if we attach a object with mass m to a spring with natural length L. Let's say if this is our spring and we attach this object with mass m, then the ODE that this object should satisfy can be written in this form. The ODE for this object can be written as mu double prime plus gamma u prime plus ku equals capital F of t. And what is u and gamma here? So u of t here is basically the equation or the position function, basically position function for mass m as a function of time, right? T is time here. And gamma, we saw that it's called the damping coefficient. Damping coefficient, which will be a positive number if we assume there exists friction. And of course, in practice, there exists friction. So if you want to solve a practical problem, then we have to assume that gamma is positive. But if we assume that in the ideal case where there's no friction, then we can assume that gamma is equal to 0. And K here is the spring constant. And it depends on the material, of the spring. And capital F of t is the external force. So we may decide to apply some external force to our system. So it may or may not exist depending on whether we have external force or not. If we don't have any external force, then we simply set F of t equals 0. And then we will have a homogeneous equation, basically. So last time we covered different scenarios. So we looked at scenario 1, where we have free, undamped system. Scenario 2, we assume that we have free, damped system. So free means we assume that the external force is 0. If we assume that the system is undamped, then that means that gamma is equal to 0, which means basically we are assuming there's no friction and gamma would be 0. And if we assume that the system is damped, then we have to assume that gamma is a positive number, is non-zero. So we looked at the solutions in each of these cases. Now, another scenario that we want to look at it this time, scenario 3. So this time we want to assume that we do have external forces. So we will call this case forced oscillation. Forced means we assume there exists some external forces. So forced. And we assume this time it's undamped. So we want to assume that there is no friction and therefore gamma is 0. So forced undamped oscillations. So forced means F of t. This time we assume it's not 0. And undamped here means that we are assuming that there is no friction and therefore gamma is 0. We can assume gamma is 0. So in this scenario, what will be our ODE? Look at this ODE. This is the general case. If gamma is 0 and f of t is non-zero, then we can write this equation as follows. So in this case, we can write the ODE equation 1. Let me call this one equation 1 as follows. So we can write it as mu double prime plus ku equals f of t. So this is a non-homogeneous second order ODE, linear second order ODE. And we already saw how to solve a non-homogeneous second order ODEs. So we saw that the equation, the solution can be written as UC plus UP, complementary solution plus a particular solution. So we saw before that the general solution for this equation can be written as U equals UC plus UP. So this is the solution of homogeneous equation. And this one is a particular solution. Now we need to find UC and UP. Well, finding UC is very easy. Just we need to replace the right-hand side with 0. And then we will have the homogeneous equation. And then we can find the characteristic equation and then solve it that way. So for UC part, we know that mu double prime plus ku is equal to 0. This is my equation. I replace the right-hand side with 0. Then the characteristic equation for this will be m r squared plus k is equal to 0. I have to use the same coefficients, but instead of derivatives, I have to use powers. So mr squared plus k equals 0. That gives me r squared equals minus k over m. And then r will be plus minus root minus k over m, which is plus minus root k over m times I, the complex number I. And we previously saw that we can call this root k over m, and we can call it omega naught, which is called natural frequency. So we can write it as plus minus omega naught I, where omega naught equals root k over m was previously defined as natural frequency, as the natural frequency. So how can we write UC? Well, again, we know that if we have two complex roots, alpha plus minus I beta, then the linearly independent solutions will be e to power alpha t sine beta t and e to power alpha t cos beta t. So here our solutions will be UC, or so the linearly independent solutions solutions of the homogeneous system will be, yes, u1 equals a sine omega naught t, and u2 equals, or let me call this one cos omega naught t, and u2 equals sine omega naught t, and uc can be written as the solution for homogeneous system. uc can be written as c1 u1 plus c2 u2. So c1 cos omega naught t plus c2 sine omega naught t. This is for UC. Now for UP, remember we have to find UC and UP, and then the general solution will be UC plus UP. Now for UP, we have to make an assumption for our f of t, because we are assuming that f of t is non-zero. But which non-zero function? Here we'll assume that our f of t, which is a non-zero function, is a function of the form f naught times cos omega t. Because in practice, many times when we have forced oscillations, the external force is a periodic function, which is also itself oscillatory. So that's why we can assume that it's a sine function or cos function with some frequency, fixed frequency. So for this reason, because the practical function, in practice, it happens that our external force is many times it can be written in this form. So for this reason, we will assume that our f of t is a function of the form some constant times cos omega t for some omega. So for UP, so let's assume that our external force is a function of the form capital F of t equals f naught times cos omega t for some frequency omega. So again, the reason that we assume this is because in practice, in many situations, we have an external form of this form, or we have a periodic external force, which can be written as a sine function or cos function. Here we assume that we have a cos function. It doesn't matter, if you even assume that f of t is a sine function, the calculations will be very similar. So now we need a particular solution. So we need a particular solution for this non-homogeneous system for m u double prime plus ku equals f naught times cos omega t. Now we want to use undetermined coefficient method to find a particular solution for this. Because the function in the right-hand side appears in our table. Remember, we said before that if the function in the right-hand side appears in our table, a table that we introduced for undetermined coefficient method, then we can use that table to introduce a guess function as a solution. But if it does not appear, then the function in the right-hand side does not appear in our table, then we have to use the other method that we learned, which was called variation of parameters. So here we need a particular solution for this. We want to use undetermined coefficient method. So now our guess function depends on whether this omega that appears in the right-hand side, this omega, is it equal to omega naught, the natural frequency, or it's different than the natural frequency. So we will consider two cases here. We are right now in scenario 3. So again, we have two possibilities. Here, there are two possibilities. So scenario 3.1. If omega is different from omega naught. Then using undetermined coefficients. So in this case, we can use undetermined coefficient method. And the table to introduce the guess function as follows. So we can write UP as A cos omega t plus B sine omega t. Remember we said that if in the table we were saying that if let's say the function in the right hand side is A cos beta t, then our guess function can be written as, let's say, capital A cos beta t plus, let's say, capital B sine beta t, which is the case here. But why are we assuming that omega is not equal to omega naught? Because after we introduced that table, we gave a very important remark that if this function here, the function appeared in the guess function, is a solution for homogeneous equation, then we have to multiply that function by t, by a proper power of t, basically. Because if this cos beta t is already a solution for the homogeneous equation, if this is already a solution for homogeneous equation, that means when you replace u with this, mu double prime plus ku becomes 0, and it cannot be equal to this function anymore. So in that case, we have to multiply our guess function with the proper power of t, which could be power 1, or let's say even if it could be in the case where t times cos beta t is still a solution for the homogeneous equation. In that case, we have to multiply with t to power 2. So that's why I'm saying that in general, we can say that if this is already a solution for homogeneous equation, then we have to multiply this with the power of t, proper power of t, which could be t to power 1 or t to power 2, depending on the example, or any power of t. But if omega is not equal to omega naught, then this cos omega t, our beta, our beta is omega here. Our beta is omega here. Now, if omega is different from omega naught, this cos omega t will not be the solution for, will not be a solution for the homogeneous equation. Why? Because we just saw that the two linearly independent solutions for homogeneous equation are cos omega naught t and sine omega naught t. So if omega is different from omega naught, then cos omega t will not be a solution for homogeneous part anymore. For example, let's say if omega naught is 2, then that means cos 2t and sine 2t will be the solutions for homogeneous equation. But omega is different from omega naught. We're assuming in this case omega is different from omega naught, so omega could be 3. So cos 3t will not be a solution for homogeneous equation anymore. If cos 2t and sine 2t are two linearly independent solutions for the homogeneous equation, cos 3t cannot be a solution anymore, because the general solution for homogeneous equation can be written as any linear combination of these two functions. So if cos 2t and sine 2t are linearly independent solutions. Any linear combination of them will be also a solution, but cos 3t will not be a solution anymore. So my point is, if omega is different from omega naught, then we can say that cos omega t will not be a solution for the homogeneous equation where the right hand side replaced with 0. And therefore, according to our table, we can use this function here as our guess function. So UP can be written as A cos omega t plus B sine omega t. And we need to find these constants A and B. So for some constants, A and B. Now to find A and B, substitute a UP into our ODE. Now, what was our ODE? It was mu double prime plus ku equals f of t, and f of t we are assuming is a function of the form f0 times cos omega t. And now we need u double prime here, and we know that this is our UP, a particular solution, A cos omega t plus B sine omega t. So we need to differentiate this function twice. Now the first derivative will be minus A omega sine omega t plus derivative of the second term, which is B omega cos omega t. And the second derivative of first derivative will be u double prime equals minus A omega squared cos omega t minus B omega squared sine omega t. Now m, as we mentioned above, mu double prime plus ku must be equal to f of t, which is f0 cos omega t. Then we will have m times this function. This is u double prime, m times this function plus ku, and u is this function, equals f0 cos omega t. So we will have minus m a omega squared cos omega t minus mb omega squared sine omega t plus this two terms are for mu double prime term. Then you also have ku term. Ku term will be ka cos omega t plus kb sine omega t equals f0 times cos omega t. Now, if I rearrange these terms, in the left-hand side, I have two cos terms and two sine terms. I want to regroup them together. So then I will have cos omega t times minus ma omega squared plus ka plus sine omega t times minus mb omega squared plus kb equals f0 times cos omega t. Now we are ready to compare left-hand side with right-hand side. The coefficient of cos omega t in the left-hand side must be equal to the coefficient of cos omega t in the right-hand side, which is f0. And coefficient of sine omega t in the left-hand side must be same as coefficient of sine omega t in the right-hand side, which is 0. So by comparing the coefficients, in left-hand side and right-hand side of this equation, we can say that minus MA omega squared plus KA equals F0, and minus MB omega squared plus KB equals 0. So this one, if I factor B out, B times minus M omega squared plus K equals 0. And then this implies that either B is 0 or this term is 0. A product of two terms equals 0. So either the first one is 0 or the second one is 0. But the second one is not 0 because we are assuming that omega is not same as omega naught. So this is non-zero since omega is not same as omega naught by our assumption. Remember, we are in scenario 3.1 where we are assuming omega is not same as omega naught. So that means omega squared is not same as omega naught squared. Omega naught squared means K over M. Because omega naught was root K over M. So omega naught squared will be K over M. And that means M omega squared minus K, or minus M. You can say it this way, that M omega squared minus K is not 0. Or we can say that minus M omega squared plus K is not 0. So the second term is non-zero, therefore the first term must be 0, which means B must be 0. And for the first equation, if I factor A out, then I'll have A times minus M omega squared plus K equals F0. And then A will be equal to, because again, this term is non-zero. We just showed that this term is non-zero, so we can divide both sides by this number. If a number is non-zero, then we can divide both sides of the equation by that number. So A will be equal to F0 divided by minus M omega squared plus K. So UP will be equal to, we said A cos omega t plus B sine omega t. And we found A and B, so then B is 0. So second term vanishes, and then first term we found A as F0 divided by minus M omega squared plus K cos omega t. Okay, so this is our particular solution. We can also write it this way. We can also write it as F0 divided by, if I factor M out, I can write it as, if I take M out, I'll be left with minus omega squared plus K over M. And K over M is omega naught squared. So we can also write it as F0 divided by M times minus omega squared plus omega naught squared times cos omega t. And then the general solution will be U of t equals UC plus UP, complementary solution plus particular solution. So C1 cos omega naught t plus C2 sine omega naught t and plus UP we just found it above, plus F0 divided by M times minus omega naught plus omega naught, omega squared plus omega naught squared cos omega t. So this is our general solution, which involves two constants, C1 and C2. And if you want to find C1 and C2, you need the initial conditions. Once two initial conditions are given, then we can find C1 and C2. So here C1 and C2 are constants. All right, now let's look at also case or scenario 3.2 if omega is equal to omega naught. So scenario 3.2. If omega is equal to omega naught. Again, our equation, let's write down our ODE again. So it was mu double prime plus ku equals F0 times cos omega t, omega naught t. If it was F0 times cos omega t, but omega is equal to omega naught, so F0 times cos omega naught. So our ODE in this case will be mu double prime plus ku equals f of t. F of t, I was assuming that is F0 times cos omega t. And in this scenario, I'm assuming that omega is same as omega naught. So f of t can be written as F0 times cos omega naught t. Now, how can I modify my guess function? So according to what we learned in undetermined coefficients method, since cos omega naught t and sine omega naught t are solutions for the homogeneous equation, what should we do if the guess function, which is generally like a times cos omega naught t plus b sine omega naught t, but here cos omega naught t and sine omega naught t are solutions of the homogeneous system, homogeneous equation, meaning that when you replace u with those functions, you get mu double prime plus ku equals 0. It cannot be equal to F0 cos omega naught t. So in that case, we have to multiply our guess function with a proper power of t. So since these are solutions for the homogeneous equation, we must multiply them. We must multiply the guess function by a proper power of t. Proper power of t. So here, our guess function would be like a times t cos omega naught t plus b t sine omega naught t. So here it's enough to multiply with t itself, because then t cos omega naught t will not be a solution for the homogeneous equation anymore. If t cos omega naught t and t sine omega naught t were also solutions for the homogeneous equation, then we would have multiplied with t to power 2 instead of t. But right now, multiplying with t itself is enough, because t cos omega naught t and t sine omega naught t are not a solution for the homogeneous equation anymore. The only functions that are solutions for homogeneous equation are these two functions. The only two linearly independent functions that are solutions for homogeneous equation are these two functions, cos omega naught t and sine omega naught t. So multiplying with t itself is enough in this case. So again, our guess function includes two constants a and b, and we need to find those constants by substituting back into our equation. So again, find the constants a and b by substituting back into our equation, which was mu double prime plus ku equals f0 cos omega naught t. So we need u double prime here, and this is our guess function, or up basically. So what will be up prime? The first derivative will be, so I have to use the product rule because I have multiplication of two functions, t and cos omega naught t. So for the derivative, I need to use the product rule. Then I'll have a times cos omega naught t minus a omega naught t sine omega naught t. So these two terms for the derivative of the first term here. The derivative of first term here using product rule will be this term minus this term. Similarly, derivative of second term, again, we have to use the product rule. Then we will have plus b sine omega naught t plus b omega naught t cos omega naught t. So this is the first derivative, and then the second derivative, up double prime, will be minus a omega naught sine omega naught t minus a omega naught. So for the derivative of this term using chain rule, derivative will be this. Derivative of second term here, we have to use the product rule. Derivative of t is 1, so minus a omega naught sine omega naught t. And then derivative of sine omega naught t, which is by chain rule, omega naught cos omega naught t times the rest. So it's going to be minus a omega naught squared t cos omega naught t. And then for the derivative of third term, we will have b omega naught cos omega naught t. And then for the derivative of fourth term, we will have b omega naught cos omega naught t. And then minus b omega naught squared t sine omega naught t. So this is u double prime. And if I simplify it, I can write it as minus 2a omega naught sine omega naught t plus 2b omega naught cos omega naught t minus a omega naught squared t cos omega naught t minus b omega naught squared t sine omega naught t. So from a omega naught, from minus a omega naught sine omega naught t, we have two of them. From b omega naught cos omega naught t, we have two of them. And from each of these terms, we had only one term, which I wrote them here. And now if I substitute back, again, remember our equation was mu double prime plus ku equals f0 cos omega naught t. Then we'll have my m times u double prime. So this is u double prime. I just need to multiply it with m. Then I'll have minus 2 ma omega naught sine omega naught t plus 2 mb omega naught cos omega naught t minus ma omega naught squared t cos omega naught t minus mb omega naught squared t sine omega naught t plus, so these four terms all together were mu double prime. Then I need to add it with ku plus ku mu double prime. Look at here. Mu double prime plus ku equals f0 cos omega naught. So plus ku plus k times at cos omega naught t plus kbt sine omega naught t. So these two terms are for ku. And then the right-hand side is f0 cos omega naught t. Now, if I rearrange the terms together, in the left-hand side, I have some cos omega naught t terms. I have to regroup them together. Sine omega naught t, regroup them together. I also have some t cos omega naught t terms. I have to regroup them together. And some t sine omega naught t that I have to regroup them together. So in the left-hand side, I will have a t cos omega naught t times minus m omega naught squared plus k. See, when I look at the left-hand side, which terms are t cos omega naught t times a constant? So look at this term. This is t cos omega naught t. And I can also factor a out as well. So a t cos omega naught t, I factored out, and then k was left. Another t cos omega naught t term is here. T cos omega naught t times a, I factor out. And what will be left? Minus m omega naught squared. So basically, I'm just looking at the left-hand side and try to regroup the similar terms together. So t cos omega naught t is one of the terms that category of terms that I can regroup them together. So t cos omega naught t, this term is t cos omega naught t term. This term also is t cos omega naught t term. So t cos omega naught t times a, because both of them have factor a as well. So a t cos omega naught t is what I'm factoring out. And what will be left? From this term minus m omega naught squared will be left. And from this term plus k. Minus m omega naught squared plus k. Similarly, for other terms, for t sine omega naught t term, I can factor b times t times sine omega naught t. And what will be left? Again, minus m omega naught squared plus k will be left. And then we'll have plus 2bm omega naught cos omega naught t minus 2a m omega naught sine omega naught t. And then the right-hand side must be f0 times cos omega naught t. Now, when I look at the term on the left-hand side, this term is 0. Because omega naught, by definition of omega naught is root k over m. So that means omega squared is k over m, and therefore m or k minus, if I cross multiply, k minus m omega naught squared will be 0. So this term is 0. This term is also similarly 0. So I will left with so what can we say? We can say that 2b m omega naught cos omega naught t minus 2a m omega naught sine omega naught t equals f0 cos omega naught t. Again, if I compare the coefficient of cos omega naught t in the left-hand side and right-hand side, and coefficient of sine omega naught t in the left-hand side and right-hand side, then we can conclude that. So by comparing the coefficients in the left-hand side and right-hand side, in left-hand side and right-hand side, we can say that 2b m omega naught has to be same as f naught, and 2a m omega naught has to be same as 0. See, there is no sine omega naught t term in the right-hand side, so this coefficient must be 0. And this coefficient here must be same as this coefficient, which is f naught. So this equation immediately implies that a has to be 0. And this equation here implies that b has to be same as f0 divided by 2m omega naught. So this is the value of a and b, and therefore up will be, up was at cos omega naught t plus bt sine omega naught t. And then this will be equal to f0 divided by 2m omega naught t sine omega naught t. T sine omega naught t. So I want you to notice that, okay, let me write the general solution as well. So general solution, u equals uc plus up equals c1 cos omega naught t plus c2 sine omega naught t plus f0 over 2m omega naught t sine omega naught t. So I want you to notice here that unlike the previous case, as t goes to infinity here, as t goes to infinity, the amplitude grows bigger and bigger. The amplitude basically goes to infinity as well. Look at the amplitude is f0 over 2m omega naught times t. So as this is a constant, and as t goes to infinity, this coefficient goes to infinity. So amplitude goes to infinity. So amplitude gets larger and larger, which is not desirable in many practical situations. For example, when you build a bridge, you don't want the oscillation to go to infinity, or the bridge would break. So in many practical situations, we don't want amplitude to go to infinity as t goes to infinity. And this is what happens if omega is equal to omega naught. If omega is equal to omega naught, amplitude gets larger and larger as t goes to infinity. And this phenomenon is called resonance. Resonance means, the amplitude gets larger and larger, and omega indicates that omega is same as the natural frequency. So note that in this case, and the amplitude is f0 over 2m omega naught times t, and this goes to infinity as t goes to infinity, and this is not desirable in many practical situations. For example, in building a bridge, and in practice, we normally try to avoid this situation, which is called resonance, where omega is equal to omega naught. So this is called resonance. If omega is equal to omega naught, and normally we try avoid resonance. And the reason I just explained why we try to avoid resonance, because we don't want the amplitude to get larger and larger as time passes. Now let's look at an example. So example, a 3 kilogram object is attached to a spring, and we'll stretch the spring to a spring, and we'll stretch it. We'll stretch it 392 millimeter by itself. Suppose that there is no damping. There is no damping in the system. And the forcing function. The forcing function of the form f of t, capital F of t equals 10 cos omega t, is attached to the object. And the system is experiencing resonance. And the system is experiencing resonance. If the object is initially displaced, displaced 20 centimeter downward from its equilibrium position, and given a velocity of 10 centimeter per second upward. So if the object is initially displaced this 20 centimeter downward and given a velocity of 10 centimeter upward, find the displacement at any time t. Find the displacement at any time t. In other words, find u of t. You want to find u of t here. The displacement as a function of time. So here the question says that and is assuming that we have a resonance. So resonance means omega, and the external force is 10 cos omega t, and we have resonance, so omega must be equal to omega naught, the natural frequency. The solution, since we have a resonance, we can say that omega is equal to omega naught, and omega naught is root k over m. The natural frequency by definition is equal to root k over m. Now we need to find k, because m is given 3 kilograms, but k is not given, so we need to find k. So need to find k. How can I find k? If you remember, we knew that mg is equal to kl. If we have the equilibrium length, which is capital L, and the length of the spring after we attach the object, what will be the new length? It says it's stretched by 392 millimeter by itself. So that's our capital L here. So capital L is 392, which is 0.392 meter. And M is equal to 3 kilogram. And G is 9.8 meter per second squared. So K will be equal to mg over L. So that's going to be 3 times 9.8 divided by L. L means 0.392. And then the result will be 75. Now that we have found K, we can find the natural frequency omega naught. Now omega naught is equal to square root K over M. So this is square root of 75 over M, which is 3. 75 over 3 is 25. Root 25 is 5. And therefore f of t, omega is equal to omega naught equals 5. Remember, f of t was 10 cos omega t, but because we have resonance, omega is same as omega naught, and omega naught is 5. So the f of t is 10 cos 5t. So our second order ODE will be can be written as follows. We can say that mu double prime plus ku equals f0 cos omega naught t. So 3u double prime plus 10 and plus 75u equals 10 cos 5t. And with the initial conditions that u of 0, the initial displacement, is 20 centimeter downward. Downward, remember, it was our positive direction according to our convention. So 0.2 meter with positive direction, and initial velocity was 10 centimeter per second upward. Upward means negative, so minus 0.1 meter per second. So the solution, we know that the solution can be written as in this form. Remember, our solution can be written in this form. So let me call this one equation star. So based on equation star above, we can write U as C1 cos omega naught t plus C2, and omega naught is 5, so C1 cos 5t plus C2 sine 5t plus F0, which is 10 over, it was F0 over 2m omega naught. So 10 over 2m is 3, omega naught is 5. T sine omega naught t. Omega naught is 5, so t sine 5t. So we can write it as C1 cos 5t plus C2 sine 5t plus t over 3 sine 5t. Now, to find C1 and C2, we need to use the initial conditions. So lastly, find C1 and C2 using the initial conditions. So we will have U of 0, which is C1. If you replace t with 0 here, this term vanishes, we'll be left with C1. And C1 was supposed to be, because U of 0, we know it's 0.2. So 0.2, so that gives me C1 equals 0.2. And what about U prime of 0? First, we need to find U prime. U prime will be minus 5C1 sine 5t plus 5C2 cos 5t plus 1 over 3 sine 5t plus 5t over 3 cos 5t. So U prime of 0 will be 5C2. If I replace t with 0 here, this term vanishes, 5C2. This term vanishes, and this term also vanishes because cos 0 is 1, but times 0 will be 0. So U prime of 0 is 5C2, which is supposed to be minus 0.1. So C2 will be equal to minus 1 over 50. So we found C1 and C2 here. Therefore, U of t will be equal to C1 cos 5t plus C2. So we had it here, C1 cos 5t, C2 sine 5t, t over 3 sine 5t. We already found C1 and C2. So C1 was 0.2. So let me replace it directly. 0.2 cos 5t minus 0.1 over 5 sine 5t. What if I wrote it as minus 1 over 50? Let me write minus 1 over 50 sine 5t and plus t over 3 sine 5t. So this is the final solution, or the displacement function. This displacement function as a function of time, basically. So these were some applications for second order ODEs, linear second order ODEs. We looked at harmonic oscillations in the free case and in the forced case. In the free case, we saw, basically we had a homogeneous equation, and in the forced case, we had a non-homogeneous equation. In each case, we knew how to solve or handle that type of equation. Okay, guys, so this finishes chapter 2.